Hi everybody. Kindly asking if we could have somebody confirm if you can hear me just fine. I certainly know you can see my screen because I'm logged on to my mobile device as well, but thank you very much. Yeah, this there's something something disturbing about this academic year and specifically this term. If you look at the plan that we had, at least relative to some of the key things that we were supposed to look at, you begin to notice that the 1 week that we have remaining is actually not going to be sufficient for us to. Today I'm making up for the Friday session when we were supposed to have a lecture or something, and then remember the other day we had an assessment or something like that, so it's very, very unfortunate things happening here. And then there was that disruption when one of your colleagues passed on or something, so quite a number of things that have happened here. And so I've been scratching my head here trying to figure out what the best possible approach would be, because it turns out that if I can maybe double back here to try and remind us of some of the things that we've done so far. If we are to double back to a lecture series, I don't know if it's module or something, lecture series number 2, where we're looking at when we're looking at the hardware pipeline and the actual lecture series number 3 and the logical pipeline. You remember that, or you notice that, and I think I mentioned this explicitly, you notice that the things that we have been doing so far are actually tied to this, right? So there's a lecture series which was dedicated to just outlining exactly how you create these different objects, right, or models ideally, right? So we covered model space. We did quite a bit here. Granted, there's some things that we've looked at here, like ideas surrounding how an image is actually rendered onto a computer screen. Technically speaking, that's part of like screen space or something. But anyways, and then what we've been doing as part of our discussion of geometric transformations is we essentially covered details associated with odd space. Okay, so how do we project, how do we transform the things that are in model space such that they're moved to odd space, right, together with other objects that would be a part of, if you think about what I'm talking about relative to our case example, which is our polyfield game here, such that we have all of those different objects in the polyfield game, right? So we covered model space. And it turns out that what we started doing, right, when we look at the 2D variation of view space here is space number 3, logical space number 3. And so all we are doing in logical space number 3 is we're saying, how do we move, from a sort of situation where we have all of these different objects in odd space, all of these different objects, to a situation where we are mimicking what a camera would actually see ideally, right? So we're moving from odd space to view space. Now, the next stage, the next thing we're supposed to do is we're supposed to have just a brief discussion of what typically happens into clip space. And my thinking here is that we can probably plan this in such a way that we have a discussion of this on Wednesday, right? I don't know. And then possibly, because on Thursday we have a test or something, possibly we can then have a discussion of screen space as a very last discussion on Friday. Now, because the things that we would ideally need to discuss, both in space number 4 and space number 6, are detailed, I wouldn't want us to rush through these things. So what I would do is I'll likely modify my slide decks in such a way that we just focus on the essential aspects of this, right? The basic concepts, ideally. We'll probably leave out anything to do with programming, so how exactly we use OpenGL to actually accomplish the things we're going to be discussing here. And in fact, when it comes to rendering algorithms, for instance, the things that the algorithms or heuristics that are used to render things onto the screen, we'll probably just look at like one naive approach, just so we have an idea of this. Very unfortunate, but we've lost out on quite a bit, right? Instead of 15 weeks, this what do you call this? This term was stripped down to 12 weeks, right? And then we lost a week here when we had that confusion. So in essence, we've literally been having classes for just about 11 weeks, but that's fine. I don't want us to rush through things and then, subject you to reading up on things that are really going to be unnecessary here. But anyways, so on with it then. I thought I would mention that. Maybe something else worth mentioning here is that there have been a number of changes. We were unable to administer quiz number 4 on Friday. Quite sad, because the venue was not available apparently. So what I've done is I've managed to secure a venue from one of my colleagues Tuesday. So there's an 8 a.m. slot on Tuesday. This is when we are going to administer the very last quiz, which is quiz number 4. There was a suggestion from some of you. I don't know how many of you were present really. After we were unable to administer the test, I think we had a very brief interaction outside the department, and there was a suggestion to say, why can we not just scrap off? I think it was one of the proponents of this was, I can't quite remember, I think our course rep here, Mr. Lubas, right? Why can we not just scrap off quiz number 4, right? So that we just have 3 quizzes. I was like, well, if that's what you want, that's fine with me, right? But I want to remind you that what we have 3 categories here, right? There's attendance in terms of the assessment. There are the quizzes, right? We're calling these labs or quizzes or something. And then we have the test, right? And if you remember, attendance is 5%, quizzes are 15%, the test is 20%, right? So if we decide to write, which we can scrap it off, I guess, but we can't. If we were to say, well, we're just going to scrap, we're just going to write 3 quizzes here. What this means here is that each quiz is essentially going to be 5 marks, right? 5 marks ideally. And obviously the performance in these quizzes that we've written so far, it's been quite bad, right? However, if we decide to spread the damage, this is the phrase I like to use here. If we say we write 4 of them, even if you got very low marks in these other quizzes, you'll be fine, because possibly you will get better marks, I think you will, in the very last quiz. This is one of the reasons why I'm insisting that we write this quiz. But also, we planned for it. I've already printed it out. Anyways, so we have this quiz, which is going to be administered on Tuesday at 8 in the Confucius Multipurpose Hall, ideally. And then I mentioned that class theory test number 1 is going to be administered on Thursday I am yet to confirm availability of a much larger venue, but in the event that the Confucius multipurpose hall is, in the event that I'm unable to secure a venue at 8, tentatively the test is going to be at 8 on Thursday. If I'm unable to secure a larger venue at 8 on Thursday, what we're going to do is we're going to see if we can find a venue later in the day, somewhere around 17. So we shall instead have this major assessment administered in the evenings, right? So just take note of the fact that for the class theory test, it's either we're going to have this test administered at 8 on Thursday, or at 17 or 18 hours on Thursday itself, but it's on Thursday. Okay. Anyways, so on with it, I guess. Now a reminder here that when we met last time, right, we were trying to understand the process that we go through to transition from world space to view space, is it? The interesting thing that came out of our discussion was this notion that the coordinate systems that are used, right, in world space compared to your viewport or something, view space or something, are different, is it? In particular, the units, right, are typically different. And also thing about this is when you are taking a photo or video footage of a particular scene, right, in a real world setting, typically a camera will use units like millimeters or something like that, right? Is it? So this is what we have here as your window size. Our interest is to try and figure out exactly how we can project whatever point falls within this window here onto the viewport. And we realize that this is something that we went through this. So it's simple basic arithmetic, actually. I don't know, it's mathematics, I guess, I don't know. But very basic math, right? But we realize that we can look at the way we're going to project this point in our window relative to the factors associated with the different ratios aligned with the window sizes, right, and the viewport size. Yeah. So all we are doing really is we are saying we're going to get for us to figure out a point in the viewport. Remember, the coordinates in the viewport are being represented by u and v, is it? U for equivalent of x coordinate and v for the equivalent of y coordinate or something. And so what we realized was that we can do this mapping using this linear equation, right? So our point u, an arbitrary point u in our viewport, right? So in essence, we're saying is that any arbitrary point in here, u, comma v, right, can be derived, because the idea here is we know the location of the point in this window here. So question is, how do we figure out its equivalent location in our viewport? Well, we essentially just use these two linear equations, ideally, right? So for the u coordinate, or the x in the viewport, what we do here is we just say we're going to get u minimum, right? And then add the scale, the ratio, right, from the window itself. Is it? If you notice here, it's a ratio between x minus x minimum divided by x maximum minus x minimum, right? If this is making sense. Because if you think about it, right, we may not know what the value of u and v is, but we know the length and the height of the viewport. In other words, the things that we know are the knowns. For the viewport, or for the window, we know the height, we know the window width as well, right? What else do we know? Well, we know the location of the point x we know the location of the point P, right? X and Y. And then for the viewport, because we already know, right? I guess the resolution associated with the viewport, like where exactly we're going to project this point, this arbitrary point, we ideally would know the width of, sorry, the viewport height. Right? Height. We know the viewport height. We also know the viewport width as well, is it? But what we don't know is, we'll call this x prime and y prime. So what we're saying is that for us to figure out x prime and y prime, all we do really is we plug in the values associated with this. And perhaps what was interesting is that we realized that using these two linear equations, we can actually come up with a 3 by 3 matrix, right? Which we can then use to multiply with the point x, y, z, if you will, or x, y, sorry, not z, because this is 2 dimension here. Our point x, y, right? So that we derive u and v. And really what we have is this, right? So using homogeneous coordinates, we realize that all we do is we make use of this sort of 3 by 3 matrix. Whenever we multiply this 3 by 3 matrix with a position in the window x, y, right? Using homogeneous coordinates, we'll be able to derive u and v. And really, if you do your multiplication here, right, of this 3 by 3 matrix and this 3 by 1 matrix here, you'll be able to get the equivalent 3 by 1 matrix, which will represent u, v, 1 idea. Right? So in other words, if we come here and we do the multiplication, I don't know if you had a chance to look at this, but if we do our multiplication of this, we will come up with the usual, is it? We'll have this, right? Sx times x, which is going to be x sx, and then we'll have 0 times y, which is 0, tx times 1, right, which is tx. So we're going to have x sx plus tx. Right? And then for the y component, what I was using here, it's like 0 times x, which is going to be 0, plus sy times y, which is going to be y sy, plus ty times 1, which is going to be ty, ideally, right? And then the last one is obvious because we're using homogeneous coordinates. The last one is just going to be 1 ideally. So 0 times x is going to be 0, 0 times y, so plus 0 times y, which is 0, plus 1 times 1, which is 1, and this is going to be 1. Now, what we're saying here is that these two equations here, right? These two equations, x sx plus tx here, right, can be, because what we're interested in, remember, come back here. If you go to our equation here, if you think about it, we know what x is, we know what y is. What we don't know is this new value tx. So if we solve for tx here, we'll end up with these two equations here. Right? Tx is going to be u minimum minus sx times x minimum, and then ty is going to be v minimum minus sy times y minimum idea. All we are doing, by the way, if you pay particular attention to what's happening here, is we're just plugging in. We're saying wherever we have sx, we can substitute it with this representation here. Where we have sy, we can substitute it with this representation. And these things we already have, right? U maximum minus u minimum divided by x maximum minus x minimum. We have these things. They're in here. Okay. Anyways, so hopefully this was intuitive. What is important here, right, is that whenever we are trying to determine the location of the point in view space from word space, what we do in 2 dimensions, what we do is we multiply whatever point we have using this 3x3 matrix. And again, the conversations that we had last time when we were discussing geometric transformations apply here, is it? We wouldn't really be, if we're trying to figure out, when we're working with this sort of matrix, we wouldn't necessarily be looking at a single vertex or a single point, but rather it's an entire object, right? So it's like you have these models in model space, you've created them in model space. From model space, you use those geometric transformations so that they are moved toward space, right? So that they are co-located with these other objects in your scene. And then from there, because we cannot view everything in world space, we just have got to view a particular segment, a particular area in world space. We want to figure out exactly what the camera is going to see. So how do we figure out what the camera is going to see? Well, in 2D, what we do is we multiply whatever objects we want to be positioned in the view of the camera by this 3x3 matrix. So in other words, again, in case this may not be very intuitive, in other words, we would have a situation where, I don't know if I have this here, but maybe not here. I want to go to our polyfield example here, if I can find it. Don't know if I'll be able to find it. Maybe not. I don't know if it's in lecture series number 3 here. Maybe not. Don't know. Goodness, we've done quite a bit here. Essentially, I know we have it in lecture series number 6 here, or module number 6. All right. So in other words, what we're saying is, remember we said this thing here is made up of, this is horrible stuff. I guess I need a way of probably use one of these local LLMs to try and figure out where do I find this or something instead of I don't know if it's in here. I think it should be in here maybe. I'm just trying to remind us. There we go. Yes, if you remember, right? We said that what we're doing is we create this object, right, in model space, and we know how to do this, right? Those primitive types we discussed, right? So, and in fact, interestingly enough, we can render this entire thing here using just triangles, right? And triangles are made up of vertices and faces and stuff. So what we're saying is similar to what we were discussing in word space. When we have this thing here in model space, for us to move this thing in word space, we have got to apply either of those different transformations. In fact, in some instances, we compound those different transformations, right? So we can scale, we can translate, we can rotate a single object ideally. We move it to word space, right? Now from word space, for us to get to view space, what we're saying is we can again use this equation here, right? So we are again multiplying each of these different points here associated with whatever object we are moving to view space or camera space. Anyways, but for us to be able to understand, we are assuming that we are doing this on a single point, right? Anyhow, hopefully this is making sense here. And then, we have a use case scenario here to say, if we were to look at this from the perspective of a polyfield example, your 2D background image here is often mapped to some texture, right? World coordinates that correspond to world coordinates to the screen viewport ideally. Okay. And again here, just to recap the 2D viewing pipeline, right? For us to move from world space to the viewport, right? We see here that the original coordinates of the object has got to be transformed, right? From model space to world space. And I guess we should have had one here as model space or something. So we move from model space going into world space, and then from world space, we apply the 3x3 matrix for us to move to camera space or view space, a viewport ideally. And then the viewport are the ones that are going to be used as a basis to actually render the individual pixel positions. More on that when we have a discussion centered around that. Again, just showcasing a visual representation of the of the transformations, right, of the pipeline itself, from world space all the way up to the viewport ideally. Okay. Now the question here is, if we can do this in 2D, which is usually very easy, right? How then does this translate to working with objects that are created in 3D space ideally? And this is actually the case for most modern day real-world applications of computer graphics, right? It's usually the case that you are working with 3D objects, unless if you're graphing, right? If you're maybe working with graphics packages, for instance, like Matplotlib. But the idea here is, what exactly do we do when we want to accomplish the same thing, ideally move from world space to view space or camera space when we're working with 3D points ideally? Well, it turns out that in 3D graphics, our problem becomes slightly complicated, because what we need to do for us to understand what is happening is we have got to kind of simulate what a camera does. Okay? And in essence, we have to simulate the behavior of the camera here. Assume this camera is moving around to gain a sense of what is located at various positions of this world space. Remember, this world space comprises of a series of objects, right? A lot of objects, ideally. And in fact, in actual sense, the camera is not the one that is moving. The camera remains static. The world is what moves, right? But, it's fine. I mean, for us to be able to understand the complexity of the problem, I guess it's best perceived from the perspective of the camera moving, not the world. Okay, so it turns out really that the concepts that we've just discussed here are still relevant to a certain extent, right? But instead of you using a window, remember we move window to the viewport here, our 3D viewing volume becomes what we introduced, if you remember, as a view frustra, right? That three-dimensional area or object we discussed not too long ago. So this is what would define which part of the 3D world you're working with is going to be visible, right? In other words, if let's say you're playing the game, for instance, depending on the controls that you're pressing, specific segments of the world are going to be in view, right, of the camera itself via the view frustra. Okay, but it turns out that we should first of all figure out a way of positioning and orienting the camera in the world, right? Remember, we're interested in seeing the things that are in world space, right? We are seeing these things that are in world space using the camera. So one of the very first things we have to do here is we position the camera and orient it appropriately within world space. Hopefully this will make sense very, very soon once we get into the gory details about this. Okay, so we position the camera, we orient it, and then what we do is we will project the 3D scene onto a 2D plane ideally, right? And this we'll discuss, I think, on Wednesday or Thursday. Wednesday, I think it is, when we look at projection and clipping and all those things, right? For now, what we're saying is we first of all need to position and orient the camera in the world, and then we project the 3D scene. Incidentally, what we're looking at in this lecture series is we're just trying to understand exactly what happens when we position and when we orient the camera into the world space. Okay? All right, so lecture is essentially going to look at the camera and transforming the world into view space idea or camera space. And in terms of the 3D pipeline, right, we see here that, and this should be a familiar diagram, I guess, familiar slide, although I use different visualizations in lecture series number I don't know if that was lecture series number 2 or number 3, or I think it was number 3, I think it was. Right, so our 3D pipeline comprises of, we have word space. If you remember what happens here, right? We are actually moving objects from model space into word space, right? Using those different geometric transformations. And then what we do is from word space we move on to view space, is it? By applying the camera transform or the view transformation, which is what we're doing in this lecture series. Okay, and then at a later stage during our discussion of progression, we'll just have a recap and maybe add on a little bit of details regarding clip space, right? So this notion that whenever you position your camera, or whenever you position a camera in a certain at a certain point in world space, you can only view a particular segment of the world. And if you remember, we introduced the concept of curling, if you remember, and clipping, is it? So it's notion that if you position your camera and some of the things are not in camera view, you can curl them or you can clip them, right? So you curl them in instances where they are nowhere in camera view, ideally, right? Or they're further away from the camera view. You clip them if part of them are in camera view and part of them are not, right? And then from clip space, if you remember, we said what we have got to do is we convert, the end result here into this cube, right? Which is represented using what we introduce as NDC coordinates, so normalized device coordinates, ideally. So we're squishing everything into this cube that ranges from -1 to 1 in X, Y, and Z coordinates. Okay, and then that cube is what is going to be projected to the screen, and we know why we have got to normalize everything using NDC coordinates. The fact that the final thing that we see on screen is dependent on the resolution of the device, right? Whether it's a laptop, whether it's a mobile device with a slightly smaller form factor, or perhaps a significantly larger screen, right? Like a billboard or something like that. I don't know. Anyways, again, we are concentrating in this lecture series. We are focusing, in terms of 3D here, we are focusing on the view transformation or camera transform, ideally. Right now, just to mention here that when you're looking at the OpenGL API, the camera ideally is always supposed to be fixed at the origin, right? So at position 0,0,0 ideally. And the idea when you position the camera is it has got to be positioned in such a way that you are looking down the negative z-axis. Now, if you remember our discussion of the right-hand rule, in essence, what we are saying is that, if you position your right hand here, I don't know if you remember our discussion of the right-hand rule here, but I don't know if there's a diagram here. Yeah, but it's just right-hand rule or something. OpenGL. I don't know how much of this you still remember, right? Yeah, something like this. So what we are saying is that I'm just going to assume this thing from Perry. Usually, some of these we can assume this is fine. This is not that bad here. I'm going to just say this image or something and open it up. Using this or something. Oh my goodness, this thing is not. I'm gonna remove the left hand here. Right? It's easier that way. right? So what we're saying is, remember with the right-hand rule, right, the positive z-axis is pointing towards you, is it? And so what we are saying is that in here, when we're saying the camera is always fixed at 0, 0, but looking down the negative z-axis. In other words, we're saying the camera would be looking down, right, the negative z-axis, because this is positive z and this is negative z, ideally, right, negative z, in essence. Anyhow, right? Right. So in OpenGL, the camera is always fixed at the origin, 0, 0, 0, looking down on the negative z-axis. But what we want, right, is we want to place the camera in word space, right? So that we're looking at, let's say, given object, maybe a cube at the origin, for instance. Okay? When we look at the, we're looking at the cube at the origin, somewhere, a hypothetical position 3, 4, 5, for instance, right? Now, what we're saying is, first to accomplish this, instead of moving the camera, what happens actually is we move the world, right? So we'll be moving the world in such a way that we will end up with a situation where the camera is going to be at the origin, looking down at negative z. So we move the camera into world space, wherever it is, and then we move the world in such a way that the camera is going to eventually end up at position 0, 0, 0, in essence, right? So the camera remains fixed. And what we're doing is we're transforming the world around it, ideally. It's pretty straightforward, I guess. And so this is the scenario, right? A hypothetical scenario that we have here, where you have a camera initially positioned in world space at, let's say, position 3, 5, 4, right? And then you have, let's say, the cube, which is at 0, 0. The idea here is because the camera is positioned at 3, 4, 5, the eye of the camera, right? Like the point at which we are viewing things is going to be at this position 3, 4, 5, right? Our goal, right, is to move the camera at position 0, 0 by transforming the world. So in essence, when we're transforming the world, the things that are in world space are going to move ideally. So in as much as our cube, for instance, in this hypothetical example, would be at 0, 0, when we transform this world so that the eye of the camera is moved to 0, 0, 0, the position of the cube is going to change as well. And remember here that the cube is not the only object we have in world space. We could have hundreds, if not thousands, of objects in world space, right? With different types of transformations ideally. Okay, so again, we're trying to transform the world so that the camera is moved to the origin, which is 0, 0, and it has got to look down on the negative z-axis. Okay. In other words, we want to accomplish something like this, right? So when we are in view space, what we are doing is we are transforming things such as the camera is positioned at 0, 0 at the origin, right? So in this hypothetical example, we've moved the camera here from here, right? You can notice the eye of the camera is here. We've transformed the world in such a way that the camera now is going to be positioned at 0, 0, 0, and everything else has got to be transformed as well, right? Because we're moving the entire world, ideally. Okay? Yeah, so because in our hypothetical example, we only have one object, which is this cube, our cube has been, ideally, it's translated and it's rotated, right, to a new position, right? And in essence, the thing that helps you accomplish this, the thing that makes it possible for you to move the world to an entirely new location, such that the camera is at position 0, 0, 0, is what we're calling the camera matrix or the view matrix. It turns out you can do this mathematically. So in essence, what we're doing, if you look at this example here, 5 here is this would be like our z coordinate, is it? Meaning that if the camera is previously at x, well, 3, 4, 5, and want to move it at 0, 0, 0, we are going to end up rotating things, right? Because z is not 0 here, it's 5. We're going to be rotating the world, we're translating the world as well. at this point, obviously, we're not really doing anything fancy like sharing and scaling, right? All we're doing for us to move the camera to 0, 0, 0 is we have got to translate the word, and then we've got to rotate the word as well. Okay, so once we do that in view space, what we have is, again, a situation where the camera is at 0, 0, looking down at negative z, and then the cube has been translated, right? It has been moved. It has also been rotated to a new position relative to the position of the camera, which is 0, 0, 0. Okay, again, this is performed using our camera metrics or our view metrics, right? This is what's called camera transform or transformation or view transform ideally. Again, hopefully as you are going through this, so you're trying to conceptualize this, a bit of higher order thinking is required here. You'll be able to remember that these colors here represent the three axes that we're working with, right? Our x-axis is represented by the arrowhead in red. The location where the arrowhead is pointing here is positive, is it? Right? And then we have our y-axis, which is red, right? And then z-coordinate, which is in blue ideally. Anyways, so we have that, right? Hope this is making sense here. Now, the question to ask here is, I mean, what is this matrix all about, right? How do we, how do we know what sort of metrics to use? And again, a reminder here that if we're saying we are using basic mathematics to essentially move things here, move the world. Remember, we're moving the world such that the camera is going to end up at 0, 0. What we're saying here is that we are going to be leveraging matrix multiplication in essence, right? So the same concepts we discussed when we're looking at geometric transformations to move things from model space to world space actually apply here. So in 3D space, for us to, this view matrix or the camera matrix that we're talking about is going to be a 4x4 matrix again, right? It's a 4x4 matrix. If we can get ahead here, give you a heads up in terms of what sort of matrix we are working with here. What we are looking at is using something like this, right? 4x4 matrix again. Okay. Anyways, so it turns out, right, for us to fully understand what's going on here, we have got to define some kind of virtual camera, right, by paying particular attention to 3 key parameters, right? We use these as vectors ideally in world space, right? So the eye, I'm going to represent this by van der bar eye. So this is the eye of the camera, the pinhole, right? Or if you're viewing if you're trying to conceptualize the camera as being you here, it would be like what you are looking at, is it? Yeah. So the eye of the camera would be the position of the camera, the target, right? Where we would want the camera to point, is it? Or so that we look at what is in the world space ideally, right? So the target, represented by van der bar target, and then the up position, which essentially is supposed to be the way that your camera is being oriented, like what is up, what is down. Because remember, when you have your camera here, you can orient it in various positions, right? Think about what you do here when you're taking photos or video footage using your phone, for instance. You can position it in so many different ways, right? Position it in such a way that you're capturing what is above you, what is below you, what is in front of you, right? What is on the edges and all those things here, right? So you have this up position represented by var up, right? Which is supposed to represent what is up, right, relative to the camera ideally. And by default, typically, putatively, in most instances, the up direction will be fixed at position 0, 1, 0. Yeah, and if you think about it, right, 0, 1, 0 here simply means that because you have the value 1 here for the y-axis, it's like you are mimicking what typically happens when a person is standing up and capturing the things that are right in front of them, ideally, right? So 0, 1, 0. And it turns out that these 3 vectors will actually define our view space, right? So in essence, a coordinate system where the camera will sit at 0, 0, 0, right? And the axes are aligned with the camera's orientation perfectly. Right? So these 3 parameters are what we need here for us to figure out what sort of 4x4 matrix we're going to use, right? To view a particular scene in word space, ideally. Okay. Again, just a visual representation of what we are discussing here, right? In terms of the axes here, we have a situation where the z coordinate is represented in blue here, y coordinate is in green, and then the x coordinate is in red. A thing to note here is you notice that sometimes, depending on how you're trying to visualize something in 3D space, there's no fixed position where you have x, y, and z here. What's important for us is to remember that we're using the right hand rule, is it? So when you start moving your right hand here, using your middle finger, your pointy finger, and your thumb here, you can easily realign or reorient these different things here. Okay, so we have the 3 axes, x, y, z. And then what we also have is we're representing the camera of the eye, which is here, right? Yeah. And then we have a target, right? A position 0, 0, 0, where we would want to move the camera, right? And then we have our up vector here, represented by y, is it? If you notice this up vector here, which is in, I don't know if this is magenta or something, is more or less like aligned in the same direction as this green vector, yeah? Which is our y. Because what we want is a sort of situation where we have our up position being represented by the y coordinate, or the y plane ideally. Okay, again, just to put things into perspective here, right, because we're moving from world space to view space, we look at the fundamental differences here. We see here that in terms of world space, we are referring to this global coordinate system where all the objects are placed, right? In our case, if we look at our polyfield example, all the objects means at any given point in time, I guess, I don't know if this is, I know there has got to be, imagine this is our world space, right? So what we are saying is that in world space, we would have all these different objects, is it? Available, right? We have access to all of these different objects. And then different types of objects here. There are flags, there are trees in the background. There are what? Fences, there are guns and stuff like that, right? There are even clouds and all that, right? So quite a number of objects that we have. So in essence, our world space is this global coordinate system where we have all these objects, right? Associated with our scene, ideally. And then the view space represents a coordinate system where we have the camera, right, at the origin. It's supposed to be at 0, 0, 0, and then it's going to be looking down on the negative z-axis, right? Positive z is towards you. You can think of positive z as being towards you. So the camera is going to be looking outwards, away from you, ideally, right? And we see here that the objects are expressed relative to the camera, ideally, right? Our interest is to only render the things that the camera is able to capture at any given point in time. So the view transformation, or the view matrix, or camera matrix ideally, will convert the world coordinates into the view coordinates. And really, if we are saying that we have this 4x4 matrix, for instance, in 3D space that can be used to move things from world space to camera space, then mathematically what we're saying is that this new position P in view space can actually be determined by getting the dot product, is it, of the position in world space P multiplied by this 4x4 matrix, right? Which is M, ideally, the view transformation matrix or camera transformation matrix, ideally. And because, I don't know if it's making sense here. Because we're working in 3D here, if we are saying this is 4x4, all we are doing is we're representing this position P in such a way that we have, I'm going to go back here. Oops, sorry about that. We are representing this in such a way that because we can't, if we have a 4x4 matrix, which is m underbar view here, just say A, B, C, D, F, G, H, I, J, K, L, M, N, or P, or something like that. The only way we can actually apply this to a point, a 3D point, is if we represent it using the homogeneous coordinates. So we have X, Y, Z, and the 1, if you remember, right? So this is what we are doing. In essence, this is being represented by the view matrix, and then this thing here is represented by the P position, right? So it's simple stuff, really. Okay. Yeah. So again, we are multiplying these two matrices ideally. And in case you are wondering why we need this view space here, it turns out that it simplifies the math required for projection, because the next thing after you transform an object from world space into view space is you've got to project it somehow, right? So that it's squished in such a way that it can be rendered onto a 2D screen, ideally, right? So in essence, what we'll be doing here is just reusing the same projection code regardless of where the camera is ideally placed. And just to rub it in here, in a real world setting, right? Let's say you're building a game or something. If we are interested in seeing different parts of the scene, is it? If we are interested in viewing different parts of the scene, I'm seeing this right now, but I want to see a completely different part of the of this scene here, because there are other things down this mountainous terrain here, down here. What I would do, in essence, is I would, well, not that I would move the camera here, but you move the world so that you see those things. So it's more or less like you're mimicking the movement of the camera, right? But in actual fact, you're moving the world, right? So the camera is kept fixed at the origin, at the same position, and what you're doing when you want to see different parts of your world is you'd be moving the world or transforming it using the same matrix idea. And what you notice here is that what you're doing, in essence, is you're doing two main things. Yeah. To transform a given point from world space to view space, all you're doing is you're moving those things and you're rotating them. You're translating and you're rotating. That's it. Now you notice here, there's no shearing here. There's, none of those things that we're discussing here. No reflection and all those things, right? All we are doing is, for us to see different parts of the world, is we just translate and we rotate. And the reason we're translating and rotating is because the camera has been, it's fixed, is it? So for us to see everything else that is not currently in camera view, we have got to move and rotate the world ideally. Much like what happens when, I don't know, right? I don't know if you go out and you're sitting somewhere outside the cafeteria or something. The world around you is moving, is it? You're static, you're like the camera here. Anyhow, it's neither here nor there. So the result here is that the camera is going to be at 0,0,0, again looking down on the z coordinates, and all the objects are going to be repositioned accordingly. Now we are simplifying this, right? Because in a real world setting, this is happening at lightning speed, right? Imagine you are playing a game here. It's like within seconds, milliseconds in some instances, right? You kill a soldier, right? You've got to transform your world in such a way that that thing is not going to be visible or something. You move forward so that you see what's down the hill, you transform your world, and you rotate it in such a way that you view those things that are there. And it turns out that there are actually interesting algorithms that can be applied to figure out, to infer, to anticipate what is actually going to be viewed, right? At some given point in time, ideally. Anyhow, it's neither here nor there. Now, the question here is, how do we determine this same vector, right? We want to try and see if we can build this, camera transform or view transformation matrix using our basis vectors, right? try and see if we can do this. It turns out for us to figure out, to derive this U matrix, we have got to compute 3 orthogonal unit vectors, right? That are going to act as representatives for our camera's local axis, ideally, right? X, Y, Z, right? So these 3 unit vectors are going to be called forward, right, and up. And really, if you think about it here, you begin to notice that things like forward here is your Z coordinate, is it? You know, forward back is your Z coordinate. Your right here would be your X coordinate, is it? Right, left. And then your up would be your Y, right? Up, down, ideally. Okay? So I want to use this, right, to figure out what the matrix is here. And in essence, it turns out that for you to compute these unit vectors like forward, right, and up, all you do, like for forward, is you've got to get the difference between the target and the eye, and then you normalize those vectors. And then for you to get the right vector, what you do is you get the cross product of the forward vector and the up vector, and then you normalize as well. I'll showcase exactly how this is done. It will make sense just now, right? And then for the var up, what you do is you just get the cross product of var right and var forward. And it turns out, right, if you remember your elementary, is it Math 101 or something? I don't know if it's 101 or 102 or something like that. They told you that when you have, I don't know how much of this you remember, you guys, but they told you that when you have two orthogonal, right, vectors A and B, ideally, if you want to get a vector that is direct perpendicular from this plane, right, represented by X and B here, what you do is you just get the cross product of A and B, right? You know this. Anyhow, right, so the cross product of var forward and var up is going to give us a vector that is going to be perpendicular to both forward and up, right? Right, at the right angle, ideally, okay? And then the cross product of var right and var forward is going to give us a vector, again, which is orthogonal, right, to both var right and var forward, right? In essence, this is going to represent the correct up position, ideally. Yeah. A little bit of kind of like abstract thinking here. You want to visualize these things or something for you to fully understand what we're saying here. Anyways, so just a visual representation of these things here. Again, we're saying that these camera axes are represented by red, green, and blue, right? So right, up, and forward, respectively. Yeah. The key thing here for you to appreciate is that we will need, for us to be able to compute var forward here, we need to get, we need to normalize var target minus var I. For us to get var right, we need to normalize the cross product of var forward and var up. For us to get var up, right, the correct up position for the camera, we need to get the cross product of var right and var forward. In essence here, var up would be your y-axis, right? For us to get the correct up position, in essence, of the camera, we're just getting the cross product of x, which is right, and forward, which is z. Is it? Because we know that the thing that is going to be directly perpendicular to var right and var forward here is going to be the cross product of var right and var forward, ideally. It's not that thing here. The same applies for var right, right? It's the reason why we're getting we normalize the cross product of var forward and var up. Anyhow, again, just a visual representation of what we are discussing here. Now, the thing here is that we are just arbitrarily making reference to things like var target and var I, you know, like if you look at this, if you look at these formulas, right, saying var forward here is going to be, we normalize var target minus var I, right? And then var right is going to be a cross product of var forward and var up normalized. And then var up is going to be a cross product of right and forward. But the question is what are the values represented by var target and var I? Right? What about var forward and var up? Is it? Or var right and var forward? Right? Well, it turns out that we can actually derive these things here, right? We're going to start off here by deriving var forward because that's the first thing that we have in our equation, is it? If you notice. Yeah? So we are saying that for us to derive these basis vectors one step at a time, first thing we have to do is we compute the forward vector, right? var underbar forward. And a reminder here that var underbar forward is going to be represented by var target minus var I. A reminder also that var target is where in world space we want to position our camera, which is typically 0,0,0, right? And the var I is going to be the current position of the camera or something like that, right? Okay? But the thing here to appreciate is that if we get the difference between var I and var target, again, in case this is going to be slightly confusing, I'm going to double back slightly here so that I showcase where var I and var target is located here, right? A visual representation of var target and var I or something like that. I don't know if this is good enough or if I can use, I don't know, which is better. Maybe this is better here, is it? Okay, this doesn't have the I, but okay, I'm just going to use this. This is fine, right? var target is this thing in, I don't know, this is pink or something, and then the var I, right? This is the eye of the camera, which is here, orange. So in essence, we are saying that var forward, is going to be the difference between the eye and the target. But it turns out that this difference here can be an arbitrary value, right? Can be any value actually, is it? If you think about it. And because it can be any value, what we need is we need to make sure that we're working with a unit vector. So if you remember again from your Math 101 here, unit vector is a vector of length exactly 1, is it? Right? And we need that for us to be able to do crazy things like rotation, for instance. Okay? And then so what we need to do here is we first compute the var forward is we get the difference, but we need to make sure that we're working with a unit vector here. For us to work with a unit vector, we need to normalize, right? Whatever value we have as the difference between var I and var target, we need to normalize it so that it's a unit vector. And again, if you remember your Math 101, they told you that for you to get a unit vector, for you to get a unit vector, right, you need the length, is it? Right? And then you're going to divide each and every point here by the length, right? But a reminder that for a 3D point here, x, y, z, for you to get the length, what you do is you get the sum of the square of x, y, and z, and then you get the square root, right? So the length of position v, x, y, z, is represented as the square root of x squared plus y squared plus z squared. For us to get the normalized, right, coordinate, the unit vector, right, v underbar norm, what we do is we just divide each of these coordinates x, y, and z by the length, is it? So v underbar normalized or norm is in essence going to be equal to x, original point x, divided by the length, which is the square root of x squared plus y squared plus z squared, ideal, right? We do the same thing for y and z. We have our unit vector. Okay? If this is making sense. Just to showcase an example here, assuming the difference between var target and var I is -3, -4, and -5, what we can do is we can compute this unit vector ideally, right? Using this equation. Yeah? We're just plugging in the values, is it? We get the length by getting the square of 3 plus the square of 4 plus the square of 5, and then we get the square root, yeah? So we get 7.07. And then that's it. We normalize by just dividing -3 by 7.07, -4 by 7.07, -5 by 7.07. And then we get these normalized coordinates, right? So in essence, this is what points from the eye to the target with unit 1 ideally. Okay, so hope this is making sense here. And then for us to compute the right vector, double back here, right? We are saying that var underbar right is going to be the cross product of var underbar forward, right, and var underbar up. And then we normalize this, is it? So we have to figure out how to get the cross product of var underbar forward and var underbar up, ideally. But a reminder here that we've already figured out what var underbar forward is here, right? Is it? We're just substituting. Okay. And again, it turns out that right vector is going it's ideally supposed to point the camera towards the camera's right. In other words, you can think of the camera's right here as being your x-axis ideally. So if you think about it again, it's going to be at the right angle, right, with the forward vector and the up vector. Okay. And if you remember your Math 101 here, they told you that the cross product of two vectors, let's say A and B, is going to give you the vector that you don't know, right? It is the third vector here, which is going to be perpendicular to both A and B. And this is ideally what we have here, right? X is going to be pointing to the right. It's going to be perpendicular to both forward and up, ideally, right? So again, for you to get the cross product, not the dot product, in this case the cross product is, we just use this formula, is it? So the cross product for the x component, for all components actually, you notice that what we do when we're getting the x component, we have got to work with the y and the z component, is it? So we get y coordinate for A multiplied by z coordinate for B minus z coordinate for A multiplied by y coordinate for B. In essence, if you remember your Math 101 here, whenever you are computing a component, this particular case x, what we're doing is we are working with y and z coordinates. When we are computing the component for y, we're working with z and x coordinate. When you are computing the z coordinate, we're working with x and y coordinates. Is it? So the y component multiplied by the z component minus the z component multiplied by the y component, right? For A and B. The z component multiplied by the x component and the x component multiplied by minus the x component multiplied by the z coordinate, the z component. And then for the z component, you have the x component multiplied by the y component minus the y component multiplied by the x component. Okay? Yeah, so the result is going to be a vector, right, whose length is going to be equal to the area of the parallelogram formed by A and B ideally, right? So if A and B are unit vectors and are perpendicular, then we know that the result here, C, is also going to be a unit vector, right? Again, your Math 101 here at play. And so we notice here that var right here has got to be normalized, right, to ensure that the right vector has a length of 1. Hope this is making sense here. And then step number 3, remember, what we're saying here is that for us to derive these basis vectors that we need, right, for us to come up with this 4x4 matrix, there are certain key components that we need, is it? Var forward, var right, var up. And what we're doing right now is we are going through a process of trying to figure out exactly how we derive these 3 different components. So the last component, right, is step number 3 here, is the up vector, right? Question is, how do we compute this camera's up vector? Again, a reminder that we're saying that in an ideal case, you would position this camera in such a way that you're mimicking what a person sees when they're standing up here, is it? In which case, the y component is going to be 1, and then x and z are going to be 0, right? So you usually would position it at 0, 1, 0. Okay? This would be like, it would be perpendicular, it would be at the right angle, right? With x and z, ideally. But it turns out that for us to get a truly orthogonal basis vector, we need to recompute the up vector, because there are instances where you may not necessarily have the camera positioned in this particular manner, right? So what we're saying is you have got to compute the up vector, and what you do is you get the cross product of right and forward. And again, a reminder here that we've already computed what right is here. So the up var up and var underbar camera in essence is going to be the cross product of var underbar right and var underbar forward. Yeah. So right and forward vectors are already at the right angle, right? Construction. So their cross product is obviously going to give us again a perpendicular vector, is it? So in essence, what we're going to end up with is a situation where all of these things are going to be orthogonal ideally, or mutually perpendicular unit vectors. Okay. And just to mention here that technically speaking, if you look at var, if you notice the equation, I'm going to double back here, the original equations that we're looking at. I had a cross product here, but you don't necessarily have to, sorry, I don't have, we are not normalizing this, is it? The cross product of the right and the forward vectors. Why? Because they're already at the right angle, they're perpendicular. And so the result is also going to be already normalized by default. So we don't have to do that. Okay, so normalization is required. I mean, you could normalize if you want, you're going to get the same result anyway. Okay? So again, just a visual representation of what we're just from talking about here, right? In this particular case, we have our right vector in red, our up vector in green, and then our forward vector here is in blue. Again, what you may want to do is kind of twist your right hand here in such a way that you can reorient it to be aligned with this, right? Using the right hand rule, ideally. Again, simply put, these three basis vectors are what we need for us to define the camera's orientation in world space. Hopefully this is making sense. I'm going to pause here just in case any questions, but as people are thinking about these questions here, I wanted to remind you that the examples that I have, the examples that I have miscellaneous. What? Mm-hmm. I'm trying to see if I can find, I think I have the code or something. Use this. In essence, you know, what we are doing here is we are saying, and this is horrible because what I did in this example is I only have one object. I think I can modify this so that I have like different objects. So I'm moving a mouse here to simulate what typically happens, right? When the world, is it? So what you can do here is you can, this is, I think I need to, what you want to do here is, when you run this, what you begin to notice is as you're moving the mouse here, you are simulating what is typically happening, where this window here is your camera, it's fixed, and the world is moving, is it? So as the world is moving, right, you know, right, forward, right, and up or something like that is what we're trying to do, ideally. I don't know. This is making sense. Okay, so if we have no questions here about the basis vectors, the next thing that we ought to do here is it's like, okay, so now that we know the fundamental components that we need for us to derive this matrix here, I mean, what is this all about? Well, it turns out, right, for us to accomplish what we want, in other words, for us to derive this matrix, I'm going to double back again to remind you that we are looking for a 4x4 matrix such that when we multiply it with any point in the world, is going to give us a result that is going to be like a projection of that same point in camera space. That's what we're doing, right? So using these three components, the question is how exactly, right, do we come up with this 4x4 matrix? This is what's called the lookup matrix, by the way, right? So in essence, what we want is we are looking for this M underbar view matrix, right, which when multiplied by any arbitrary point in world space is going to give you a point, a corresponding point in your viewport, right, which will be represented by the view coordinates. And the interesting thing about this new point is that it's going to be relative to when a camera is positioned at the origin, looking down on the z coordinate. Okay, so if you think about it then, for us to accomplish this, we just need to do two things here. We must move the world, right? So that the camera is positioned at the origin, right? Because that's what we want. It has to be fixed at the origin, looking down at negative z. Okay? So we must move the world, and if you remember, moving is really translating, is it? We move points by translating them. That's one thing. And then we must rotate the world, is it? So that the camera's axes are aligned with the world axis. This is all we do here. We do two things. We translate and we rotate. Okay? So I'm going to build this thing step by step. So, right? So we begin to notice here that, and again, I'm going to double back here. Right? We're translating by I, right? I'm going to double back here to showcase something. The image that has the eye and the target, is it? We are translating the camera, right? Let's say the camera is somewhere here. We're translating this in such a way that this has got to be at 0,0. And if this is going to be at 0,0 here, it's more or less like we're translating by I, is it? By the I, the location of I. E-Y-E. Yeah? Don't know if this is making sense. So we are essentially moving, or we are translating by I, right? Now the reason why we're translating by we're saying negative I here is because if let's say the camera is currently positioned at I, for us to move it at 0,0, we subtract I, is it? Which is why we're translating it by negative I. Right? In essence, this I here is a point, it's a vertex, represented by coordinates. We can view these coordinates as being I underbar x, I underbar y, and I underbar z here. So we want to move these three coordinates to 0,0. Right? In essence, what we are doing is we are adding negative I. We're subtracting, isn't it? If we are saying the camera, I don't know if this makes sense, but if we are saying the camera is at, yeah. I should have drawn this. I should have clipped it, I guess. It would have been a lot easier, I guess. I don't know. I'll clip it. Let me clip it. I'm just going to clip it here so that I don't waffle around or something. I'll crop it, clip it, crop it. Okay, and then I'm just see if I can annotate this or something. And I'm going to double back to where I was here. It's a lot easier that way instead of moving around, right? So what I was trying to say here is that, there we go. But where is it? Ooh. I want to move it somewhere here, right? What I'm trying to say here is if this is our eye, right? Our eye. Yeah, I can't properly annotate in thing here. Forgive me, but try and see. I think I can though. I, X, comma I. I'll call this E, but it's I. We know it's I. And then this is In essence, what we're saying is, see, the camera is currently positioned at this position, right? At I, is it? I represented by EX, EY, and EZ. But we want to move it at some position. This is the target here, this position. The target position is supposed to be 0, 0, something like that, right? It's the origin. Let's just say it's the origin. It could be 0, 1, 0, something, but this is the origin. Now, for us to move to the origin, what we're saying is we must subtract from EX, EY, EZ. We subtract EX, right? In other words, we are adding negative EX, negative EY, and negative EZ. Now, when we do that, we're not moving the camera per se. We're translating the word such that this I is going to move to target. And the moment we're translating it in such a way that this I comes to 0 at the origin here, everything in word space is going to be moved by the same factor, which are essentially the things we're moving them by is negative EX, comma, negative EY, comma, negative EZ. That's what we are saying here. And we know that, from our discussion, we know that translating something is essentially just adding, right? We are adding. So to an arbitrary point, x, y, z, we are adding negative EX, negative EY, negative EZ. So in essence, we're going to have x, an arbitrary point, x, y, z, when translated by I is going to be x minus IX, y minus IY, z minus IZ, ideally. Is it? Now we're done, right? We've translated. This is pretty easy here. But the interesting thing here, right, is we know that if we want to be working with that 4x4 matrix, right? Remember, I'm going to double back here. Remember that we are doing this because we need this matrix, 4x4 matrix, that is going to be used to multiply to any arbitrary point in world coordinate x, y, z, but there'll be one here if you're using homogeneous coordinates, right? So it has got to be represented by a 4x4 matrix. And remember where we had discussions of a 4x4 matrix? I think you do, right? I know I do. In here, we said that when we are translating a point, where are you? A 3D point, we can do that using matrix multiplication, right? By using, we derived it together actually in 3D. I'm going to go back to where we have 3D here. But where are you now? There we go. In 3D, what we do is we work with this matrix, is it? This 4x4 matrix, right? You remember this? So for us to translate by I, this is what we're interested in doing, we need a 4x4 representation that's going to translate by I, right? So in other words, we are translating by I, so Tx is going to be negative Ix because we're translating by I. Ty is going to be negative Iy. Tz is going to be negative Iz. And then we have one here because it's a homogeneous coordinate system. So in essence, right, again, a reminder here that this view transform or camera transform does two things. It translates and then it rotates. What we've done here is we've solved one out of the two pieces of the puzzle here. We figured out how exactly we're going to translate. We now have to figure out how to rotate. When we have the translation and the rotation 4x4 matrices, we multiply them and then we're going to have our M under view matrix ideally. That's what we are doing here. Okay? So anyways, go here, get back to, and really you can kind of like derive this if you wish, right? If you want to derive this, if you multiply this by x, y, z, like we did, and it's going to be it's going to be homework for you guys. If we multiply this by an arbitrary point x, y, z using homogeneous coordinates like this, you will actually derive what you want, right? You're going to derive x minus ix, y minus iy, and z minus iz, in essence. Don't know, maybe not. Anyways, I was thinking we'd finish by now. So the next piece of the puzzle is we need to figure out how to rotate this camera, right? Yeah? Again, remember that when we are moving from world space to view space, the only transformations we're performing are translation and rotation. That's it, right? Because in essence, we're trying to realign the world, or we're trying to get to a situation where the camera is going to be at 0, 0, 0. It's going to be at the origin. So the only things that we are doing, transformations we are doing here, is we move things and we rotate things. Okay. Anyways, so the question is, how do we rotate, right? Well, we now have a situation where, using the translation matrix, the camera is at 0, 0, is it? But it turns out that our orientation of these axes are currently arbitrary. If you're just randomly placing a camera in world space here, it could be placed in such a way that, I don't know if I can do this, I'm not really good at drawing here. It could be placed in such a way that, if I can mimic what a camera is like here, right? How do we draw a camera here? Something like this, right? I don't know here. Something like this or something. So no, how do you usually draw a camera? Something like this or something. So it can be positioned like this, it can be positioned upside down or something, right? So we need to realign this camera, right? We realign it so that it's aligned with the world axis. So the things we have got to do here, simple stuff, I guess maybe, I don't know. But the right vector must become the world's x-axis, is it? Remember, right represents, right is x, obvious, right? Right hand rule here. Up is y, right? And then forward is z or something. So our goal in terms of doing this realignment, aligning the camera with world axis, is we've got to align them in such a way that we are rotating the world. Remember, the camera is fixed here. We are rotating the world such that the right vector, right, the camera's right vector is going to be aligned with x-axis, or will become the x-axis. How do we do this? Right is x, right? So just 1 here for the x, and it's 1, 0 here. And then the up vector becomes the y-axis, 0, 1, 0. And then the forward vector is going to become the negative z-axis, because remember, we're always looking down the negative z-axis, is it? Positive is towards you. If you think of the camera as being you, your eyes or something. If things are being moved closer to you, right, that's positive. They'll be big or something like that. Looking down means you're looking further down here. In other words, I don't know. In other words, right, this, right? I don't know, this thing, again, the way I've implemented this here. You understand what I mean, right? Right. Up, I guess, up or something. And then as you are moving, you can move further away or close or something like that. I don't know. You know, if that makes sense. I don't know what that is here. What is happening here? What? Uh-oh, I don't know what I've done here, colleagues, gentlemen and ladies. Whoa, I hope I haven't closed. I don't know what I've done here, but Christ. You guys, I don't know what's happening here. Go in view. Oh, there we go. It's gone now. Thank you. I have to push this thing back in full presentation mode or something. Anyway, sorry about that. Sorry for the mishap. It doesn't matter though. Anyhow, that's so we need to do this, right? Well, so what this rotation matrix is going to do is it's going to enable us to map a set of basis vectors to standard axes, ideally, right? And we'll have like these rows equal to the basis vectors, right? And a reminder here that when we multiply the matrix by a vector, the dot product of the first row gives the projection onto the first axis. In other words, assuming we want these new x, y, z coordinates here, when we get the dot product of this, right, matrix that we're interested in with the existing coordinates, is more, what we're doing is we are computing, when we do a dot product of this row here, we're computing the x, right, rx times odd x plus ry times odd y plus rz times odd y, odd z, or something like that. Is it? That's what we're doing. And if you notice, these things are lined up in such a way, this will make sense just now. We'll go over this again. These things are lined up in such a way that, remember we said R is supposed to be aligned with X. Up is supposed to be aligned with Y. Right? Forward, right? Forward, back, right? It's supposed to be aligned with Z, right? R, U, F, or something, right? They're aligned appropriately. Anyway, so the matrix, ideally, that does this, that does the rotation. Remember, this is 3 by 3, right? For us to be able to do this, if you remember our discussion of rotation, we said we can use a 4 by 4 representation, is it? Right? This has got to be, remember, I don't know again if you remember this, but we said that when we're doing those derivations, scaling and things like rotation can actually be performed using a 3 by 3 matrix, right? Easy. However, that linear transformation we introduce as translation is a bit odd, right? Because we're moving things. So for us to have the same dimensions of this matrix, we use homogeneous coordinates. So in as much as this may work here, the equivalent 4 by 4 matrix, which does the same exact thing, is this, right? And through to that, if you do your thing here, you get the same result as this, right? If you multiply this by your x, y, z, 1 coordinate, right? A point, ideally. So in other words, what we're saying is that the matrix that we need for us to perform rotation is this. Again, I don't really have to remind us about what happens here. Is it like a first row? If you get the dot product of the first row with a point x, y, z, right, you will get the new point x. If you do the same thing with this row, in other words, colleagues, gentlemen, ladies, what we're saying is that if you have a point x, y, z, there's be 1 here. This, right, is going to enable you to derive the x coordinate, right? And then this is going to enable you to derive the y coordinate when you get the dot product of that. And then finally, I guess, I don't know, this is going to enable you to get the z coordinate. And of course, this additional dimension we call w is, when you multiply it by this, it's just going to give you 1, right? That's what we're saying here, I guess, if that makes sense. Again, the rotation matrix is orthogonal, right? So remember, these things are perpendicular to each other, right? So orthogonal, meaning that the inverse is going to be equal to the transpose, ideally. And it turns out that it's going to be correctly aligned with the camera axis, which is what we want, right? Now, the thing to ask here is, what is Rx, Ry, Rz, U, and stuff? Well, we can derive these things, right? We can derive these things, and I think I have derivations here, more derivations here, right? So the actual rotation matrix that we have got to utilize is M underbar view here, which is the result of rotation and translation. So when we multiply rotation and translation, we're going to get this, right? And this is what we want. Ideally, when we multiply this 4 by 4 matrix with any arbitrary point in word space x, y, z, comma 1, right? Because it's like homogeneous coordinates we're working with here. We will be able to figure out exactly where it's going to appear in camera space. So this is what we need, ideally, right? Okay? Well, I guess the question we should be asking now is, what are these things here? We know what R, U, F are here. This is trivial here, but what is dot R, comma I, what is dot U, comma I, what is dot F, comma I, and stuff, right? Well, so we'll go through these things one at a time here so that we understand. I think I have all of them or something, almost there. It's good. So a reminder here that the dot product, well, dot R, comma I here, we're just getting the dot product of R and I, ideally, right? And if you remember, all we are doing here is we're just doing this multiplied, but by the way, these are represented in, this is what? Column major form, right? We've been using row major form. There's a difference. The dot product of A and B here is going to be this. It's going to, in case people have forgotten here, I had mentioned that I use row major form, right? So what we're doing here, when we have a position AX, AY, AZ here, it's like this, is it? A underbar X, A underbar Y. Let's not veer off the convention. A underbar Z, right? So we're going to be getting the dot product of this and B underbar X, B underbar Y, and B underbar Z, right? It's just that in this particular example here, the coordinates A and B, well, I didn't really represent them in row major form, but it's the same, right? This, we can multiply these things using column major form or row major form. It doesn't matter. Just have to make sure that if you're using one notation, you've got to reconcile them with the other things you multiply them with. But anyways, so the dot product of A and B is going to be A times B plus A times bx times A plus A x times by plus ax plus bz. Ax times by plus ay times by plus az times bz. Ideal. That's neither here nor there. Okay? Hope this is making sense. This is a dot product, and what we're doing here is measuring how much one vector projects onto another, ideally. So when we apply this M underbar view here, right, in essence, getting the product of the rotation and translation vectors, 4x4 vectors here, to a point, the translation is going to be applied first. Remember the order here, right? This, when we have R times T, we're saying we start off by applying translation, then rotation. So we're going to translate on I first, and then we rotate on R, right? Then just showcasing the result of just one component. I'll let you guys, let's try and see if we can figure out the other components. Just look at one component here, right? So if we have the point x, y, z, 1, right? After translating, right? What we are going to end up with here is, because we're multiplying this, is it, by the translation vector. After translating, right? We are going to end up with this, right? P prime, x minus, we've done this, x minus ix, y minus iy, z minus iz, 1 idea, right? And then what we do is, we then, we apply the rotation matrix, is it, to this. Now, again, the rotation matrix, you notice here, all we are doing is, these Rx, Ry, Rz, 0 are coming from, I'm just saying one component here. They're coming from this rotation matrix here, right? So when we rotate, right, we shall end up with x view, right, is going to be this. Now, here is the thing here. What you begin to notice is that what you have here, what I've derived here, right? Rx times x, ry times y, rz times z, plus, it's negative here because it's a negative value here, I don't know if this is making sense, you guys, but maybe not. Observe. Maybe not, don't know. Let me see if I can find a nice, I found it, something. Observe. We're saying when we translate a point x, y, z, we're translating it by, what y? We're translating it by multiplying the translation vector, which is this. I'm going to go back here. This, right? When we translate this, I don't have to redo this. We're translating, in essence, we're multiplying position x, y, z by this so that we derive this. Right? So when we translate, we shall end up with, but what is happening now? I'm going to move it somewhere here. Goodness gracious. When we translate, we're going to have x minus ix y, but guys, I don't know if it's my thumb here, I'm using touch screen or something. It's a huge ass thing here. X minus ix, y minus iy, z minus iz, and then we have the 1 here. So when we translate the point, we have this. And then what we're trying to say here is that when we rotate, right, because we're saying that we're rotating using this, when we are rotating, in essence, we get this thing, right, that has rx, ry, rz, and 0, right? And then we have stuff here. I'm not going to write this. So in the slides, what I'm saying is we're showcasing how this is being done, is it? For us to get the new x, right? Once we apply the view transform, we translate and we rotate. We've translated, this is the result. For us to rotate, for us to rotate, for us to get the upper part, the x component here, is going to be rx times x minus ex, which is, well, I guess, rx times x minus ex plus ry times y minus ey. You get where this is coming from here. Plus rz times z minus ez or something. And it turns out that, plus 0. And it turns out that this is what we have here, is it? Right? So this, look at this. Rx times x minus ex is going to be x times rx, x times rx, right? Minus r times ex, right? We've moved it elsewhere here, rearrange these things. And then we're going to, at some point, we're going to have r times y, which is going to be r times y. Then we have r times z or something. So if we reorganize these things, what we are saying is that we essentially end up with a dot product of r and p. You understand this? Right? Minus dot product of r and I, ideally. That's it. That's the representation we have. If this is making sense here. Right? And so we notice here that the constant term in the matrix here is going to be r, the dot product of, or negative dot product of r and I, ideally. So the same logic applies to these other things. I mean, it's going to take a while here for us to recompute, right? We're doing the same things over and over again. So we do this for Rx. We also do this for these other components, is it? Here. Guys, up is Y, this is U, and then this is for F. We do the same thing. We're going to end up with the same things, ideally. Okay? And then maybe just for good measure, just to showcase like some example, right? If we have our camera located at 3,4,5, it's beautiful, right? And R is equal to 1, 0, 0, right? So we want to use the x-axis here, right? The camera's right is going to be towards x-axis ideally. We're aligning them properly. Then you notice that R, the dot product of R, comma I here, we're just plugging in the values. I don't know if you're seeing here what we're doing, right? We're just plugging in the values, right? So we're going to get the dot product of R and I ideally is 3 times 1 plus 4 times 0 plus 5 times 0, right? We get 3 here, ideally. Okay, so this so the first row translation component will ideally be -3, right? Because we're looking down negative value here. It has to be negative. Right? We're subtracting 3 from 0. If you get what we're saying here, you're previously here, right? For us to move to 0, we have got to subtract 3. So this has to be negative. Anyways, and then you notice here, if you plug in the values for U and F here, you'll be able to get -4 and -5 here. But this obviously has got to be a negative value. So because negative dot here is going to be +5. Negative 5 is +5 ideally, and then would have aligned everything appropriate. And then so you can do that the same thing, right? You probably want to work it out. I do encourage you as homework. Just let's try and see if we can do this derivation for U and for F. Is it? We've done for R for this row. Let's do this row and this row, right? And you can ignore this because it's always going to be 1 here. Right. Again, so this, ladies and gentlemen, right? This is the metric transformation for a point from word space into view space or camera space. This is what we use here. Now, I wanted us to go through the OpenGL code here, have a series of code here, but beginning this lecture series, I guess we're just going to, we're not going to be examined on this or something like that, right? On the code aspect of the spaces beginning camera space, right? So camera space, clip space, indices space, and I guess screen space. We're just going to look at the basic concepts. We don't have to rush. For those of you that are interested though, what I may do, and I'm saying may here, because I think there's some people that are doing this in their project or something, I may create offline screencasts for the programming parts of the lecture series from here until the end, right? So in as much as the slides have the code, what I've included code really for just 2 module files, by the way, right? To try and put the point across here in relation to what it is we've been doing. But yeah, I guess this is yeah. Are there any questions, by the way? Let's not rush this. Don't know why they said 12 weeks, but that's okay also. It's a lot though that has happened also. Yeah, I mean, maybe just FYI here, I'm just going to cruise through just because they're in the slides, but just FYI in terms of the implementation. Again, we will not be examined on the implementation of view space, clip space, view space / camera space, clip space, anything to do with projection as well. Orthogonal progression and all those things, and also screen space, right? In terms of the programming part. But the basic concepts we have got to discuss these things here. But so in OpenGL, again, there are built-in functions that can be used to implement the things that we've been discussing. I don't know if this is even necessary here, because this is what comes next is just the code here. Just okay, we're going to pause here. I guess I wouldn't want to confuse people here, but maybe just to draw attention here to some of the fundamental differences between 2D viewing and 3D viewing, right? Remember, we did two things here, right? We're dealing with this view frustum here, where we're translating and rotating in 3D view space or camera space. But when we look at 2D space here, all we're doing is our transformation is quite simple, right? If you remember, we have this window and then we have a viewport, and we have that linear equation that does something that is seemingly trivial. This, ladies and gentlemen, this, boom, right? That is it. This is all we are doing. I don't know how many of you have been kind of like paying attention. What's happening here, right? You remember what Sx and Sy is? This is what we're saying. This is like the derived 3x3 matrix for 2D viewing, right? It's homogeneous matrix. But guess what? Before we get to the actual summaries, right? Guess what, ladies and gentlemen? Surprise, surprise. Observe. And I hope I'm here. Surprise, surprise. Okay, this is, I'm going to go to 2D because it's the 3D geometric transformation, is it? We're going to go to 2D. You remember this, colleagues? Ladies and gentlemen. I don't know how much of this you remember here, but boom. You see this? In particular, I want to draw attention to this and this. Is it? Boom. And then you remember this? This. In 2D, right? This and this, right? Surprise, surprise. Okay. And I want to draw attention to this. I just want us to just do a recap in terms of the summaries when we're looking at 2D viewing and 3D viewing. By the way, you can play around with the 3 examples. I've pushed them to GitHub also. But in terms of the summaries here, right? Our window, when we are working in 2D, right, 2 dimension, is a rectangle, is it? With just those 2 dimensions, right? X and Y, is it? Which is mapped onto a viewport, which is a rectangle on the screen, U, V. However, in 3D, we are looking at this view frustum, right? The volume, because 3D world here. But our viewport is the same as 2D, right? It's a rectangle as well. We're going to be discussing just basic concepts of clipping on Wednesday, and probably Friday or something, I don't know. But in terms of clipping here, we're clipping against the 2D window, and then in 3D viewing, we're clipping against the 3D frustum. So everything or anything that is outside of our view frustum has got to be curled or clipped. You remove it, chuck it out. And then the matrix forms, right, we are using, right? In 2D viewing, it's this. Okay, this is not properly. This is, again, this is in column major form, right? It's Sx, 0, Tx, right? Right? 0, Sy, Ty, 0, 0, 1, ideally. Is it? If you remember. And then for 3D viewing, we are using this lookup matrix, a 4x4 matrix that we're just from deriving. And then the result, right, is we are transforming a point x, y into its equivalent position in screen space U, V. In word space, right, we're getting a point x, y, z. We are going to project it in view space in x, y, z as well, right? So there you go, right? Some of the differences. And then in terms of transformations, I forgot here, for 2D viewing, you just have those affine transformations, right? You're scaling, you're translating and stuff. And then for 3D viewing, there's a bit of perspective transformations, right? Or perspective progression. So when we look at clip space on Wednesday, I believe it is, we're going to be looking at exactly how we play around with orthogonal projections and perspective progressions here, right? And when you combine them with our affine transformations, translate and rotate, if you remember. So what we're saying here, in 3D viewing, we are adding the concepts of the camera position, is very important, and its orientation, right? And then there's supposed to be a projection, which we'll discuss in the next lecture series here. Guys, I do encourage you, so what comes next here, right? What comes next here is actually just an outline of the implementation of 3 chunks of code. There are just 3 of them. There's a static camera, right, which showcases ideally just we're trying to come up with an implementation of like a static camera at position 0,0, right, viewing this cube or something. And then I have another implementation where we have some orbital camera, right? So when you're moving your mouse here, but why is this not working again? When you're moving your mouse here, kind of like it orbits, right? It moves, yeah? It moves, okay? By the way, for this to go away, you need to, for the other one, you need, no, not, for the 2, you can click the X, but for the last one, where we have some kind of like visualization or something as you're moving it, right? You'd have to click on escape for this to exit, right? So these are the 3 implementations I wanted us to go through, but at your own time, you can just play around with them. We're not going to examine you guys on this here. Just to mention that towards the end here, I think I'm mentioning that when we, I don't know why this is, when we, yeah, so we are going to, so this is what we looked at. Forget about the implementation part and camera movements, AL, spin and all that. Forget about that stuff. We don't have to force things down your throat here. It's quite unfortunate though. But just to mention, right? We looked at 2D viewing and 3D viewing and some camera parameters that are important, right? For us to kind of like build this open geocentric or anything to do with that applies to the right-handed rule here. But open geocentric 4x4 lookup matrix, right? That's it. We did not really look at camera movements and the implementation associated with that here. So what we're supposed to do in the next lecture series on Wednesday, also I want maybe just to kind of see if I can combine our discussion of clip space and also screen space just into one, right? So that we don't have a situation where we are wanting to organize makeup classes over there. Can we have a makeup class over there? I guess, I don't know, study break or something. I don't know. I don't think that would be wise here. But guys, I wanted to find out if there are questions. Sir, could you please share with us via email as well what won't be examined for us to? Yeah, sure, not a problem. But I also share this recording and a template guide for what to expect in the exam. Okay, a template or guide will be in the test. What I'm going to do here is we're going to set up the test in such a way that it's going to mimic a smaller scale version of the exam. So that will be a good enough template for you. Guys, I know probably most of you are just here to say, let me go and register myself or something. I'm taking you in a course for 792. I'm going to change things here. Midway through, there'll be like simple questions and then I'll be tracking, collect data here. And if you don't respond, then we know that you're not actively participating in the course or something. If there are no questions, we have a test on Tuesday, a quiz rather, on Tuesday. It's at 8. It's in Confucius. And the reason I'm saying this is I know there are going to be people that are going to come out of the woodwork here. No, sir, I didn't write the assessment, right? Nobody's going to give you a deferred assessment just because you decide not to show up, right? Certainly not me. I'm sorry. I'm not going to do that. I only give assessments, make-up assessments. Sorry, deferred, actually, not make-up assessments to individuals that were genuinely not able to attempt assessment. With that being said, in the study break, possibly on Monday or Tuesday, I will send out emails about this maybe by Thursday or Friday next week. I'm going to invite all of those that qualify for deferred assessments. Those are the quizzes. There are quite a number of people that were unable to write quiz 1 and I guess quiz 2 or something. So we're going to do this together or something. I'll make an announcement on when this makeup is going to be administered. Thank you very much. Quiz at 8 on Tuesday. You will see me in Confucius. Bye.